So good afternoon. My name is Tony Martin. I do mobile equipment maintenance training on a contract basis, and Delphi is one of my contracts, if you will. And today's webinar, Tech Tip Thursday, is related to voltage drop testing, which everybody hears and talks about quite a bit. Not everybody understands it fully. My purpose today is to make sure we don't leave any stones uncovered. In other words, if we're starting at the very beginning, we're starting with voltage itself. What exactly is it? And why is it such a crucial quantity in electrical diagnostics? So we're going to make absolutely sure that everybody's got an idea of what voltage is, and then we're going to take it from there and work our way up into diagnostics. But we're starting right at the very beginning today. For those who are already familiar with the subject, please be patient. For those who are very beginners, you're in the right place at the right time. So hopefully this is going to solve or maybe take some of the mystery out of a subject that, again, we talk about repeatedly and sometimes assume that people know more than maybe they do. I will tell you that I am constantly learning. Every time I go to an electrical class, there's something new that somebody comes up with that just is a worthwhile thing to know. And I try to I try to assume that nobody knows anything about what we're talking about. And so I'm not going to talk over people's heads. Hopefully, I'll be meeting you where you're at. So again, thank you very much for your participation today. I'm just going to take one last look at our Q's and A's. Can you please switch off the view of yourself? Okay. All right. So I'll do that. So I'm going to have to stop sharing just for a moment. Let's do that. So stop that. Just a second. Oh, hang on. So I'm going to stop sharing. All right. Now, let me share again, but this time I'm going to do content only. And okay, so a little bit of feedback. Is that better? Is that working better for you guys? You can see in the square window, top right corner. Good. Okay. Okay. That's great feedback. Thank you very much. So you can still see me in the top right corner, and that's all you need. You don't need to see me down below. Good. Okay. We've got some good bi-directional information going here. So I surely appreciate you guys and taking the time to help out with that. And it sounds like we're a go. So let's get underway here. Today, what we're talking about, today's agenda. What is voltage? What exactly is it? And then in turn, what is voltage drop? Why is that something we need to be paying attention to? We're also going to talk about how voltage drop affects circuit performance and why is it that we're having to diagnose it in the first place. The root causes of it all, how to measure it, and then figuring out where those voltage drops are taking place, trying to narrow down, is it on the power side? Is it on the ground side? And then finally, we're going to discuss a little bit about heavy duty vehicle, in particular, heavy duty vehicle starting and charging systems, and using a carbon pile tester for measuring voltage drop on those circuits. So that'll be the last item before we wrap it up today. Starting right from the very beginning, what is voltage? And it's very helpful for us to use a hydraulic analogy when we're talking about this. Electricity in general. If you can you can visualize hydraulics, you can visualize water flow, for instance. It's much harder to visualize the flow of electrons through wires and switches and electronic components. Many of us, maybe all of us, are visual kinesthetic learners, and we learn best when we can see things and we can get our hands on it. The unfortunate part about electricity, of course, is that if you see it or feel it, there's something seriously wrong. So under normal operational circumstances, you don't see anything. And consequently, it's really difficult to visualize what exactly is happening inside the circuit. So using hydraulics as an analogy or a way of illustrating how electricity works is a very good way of going about things. And I'll demonstrate that right now, starting with voltage. Again, this is only 1 hour long. What we're going to be focusing on is just voltage itself. If you take a look here, what we have effectively is a water tower. And the water tower has a downspout and an outlet on the lower right. There's a valve that's closed on that lower right, and there's no flow coming out of this pipe at this point. There's no water flow whatsoever. It's confined fluid is what it is. The fluid itself, let's say it's water, it will develop pressure in the system. And that's what the pressure gauge is for, is to tell us what is that pressure. The taller we make the column, the water column, the more weight is involved and thus raises the pressure. And then there's also atmospheric air pressure working on the surface of that water that's also causing pressure to be developed, if you will. So the taller the column, the more pressure you're going to build. And while there's no flow going on, yes, there is certainly pressure and potential for flow to take place. And this is basically what voltage looks like right here. Okay, so it's basically electrical pressure. So if you're thinking about pressure in hydraulics, you're thinking about pounds per square inch, kilopascals as units of measure. Where voltage you measure in volts or millivolts. Those are the two most common quantities, or pardon me, units of measure that you will be using when you're doing electrical diagnostics, volts and millivolts. But voltage is electrical pressure. If there's only one thing that you take away from this talk today, this webinar today, this should be it right here. If you can remember, just remember that voltage is electrical pressure. You can figure out from there what flow is, current is, that is. Resistance also makes sense. But remembering that voltage is electrical pressure is an absolutely critical concept everybody needs to be familiar with. And in this case, okay, pressure, we're using bar, okay, in this case. So you've got a gauge there that's measuring in terms of bar. This is gauge pressure we're talking about. It's not absolute pressure. Here we are with 1 bar is effectively the same as 14.7 pounds per square inch absolute. Okay. And one way or another, okay, this is measuring in bar, but again, voltage is similar. It's pressure, electrical pressure, and it's measured in volts. Another way of considering this or visualizing it is the idea of a water pipe, elevated water pipe, that's flowing water onto a water wheel. And that water wheel in turn is converting the potential energy. So you see this 12-volt line, okay, where the water is exiting from that pipe. So the electrical potential energy, hydraulic energy in this case, potential energy, is being converted into usable power or mechanical energy as it flows across the water wheel. And as it's dropping, it's losing potential energy. That potential energy is continuing to be converted into mechanical energy. And by the time it reaches the surface of the water below, we'll consider that to be 0 volts or ground. So Visualize this in terms of the 12 volts representing the battery positive post, and the 0 volts as being the battery negative post. And as the electrical current is making its way through the circuits, or the electrical system, it is going from a high potential energy at 12 volts, and as it works its way through, that potential energy is being converted into usable power. And then finally, when it reaches the battery's negative post, that's when it's basically at 0 volts, and we'll call that ground, chassis ground. Well, no, pardon me. The battery electrical, pardon me, the negative post needs to be considered to be 0 volts, not the chassis, but the battery negative post. And there's a reason for that, and it has to do with voltage drop. More on that in just a little bit. Think about it also, the hydraulic analogy. Here you have a tap in the restroom someplace, and right now we have pressure, we have potential energy that's there, but we don't have any flow. The reason we don't have any flow is because of excessive resistance or opposition to flow. In this case, infinite resistance. Both the hot and the cold taps are closed completely. There's no flow, but we still have we still have hydraulic pressure behind the taps. Now, if we lower the resistance in the circuit, now we're going to have flow take place. There's still pressure there, but now we have flow because the resistance has been lowered to the point where now water is flowing out of and now we have current, okay, which we would measure in amperes, using electrical units of measure. In hydraulics, we would use gallons per minute. But if you can visualize gallons per minute flowing, then you can just as easily visualize amperes or current. Same basic idea, okay? Can you have current without pressure? The answer is no. Can you have pressure, pardon me, without current? And I'm going the wrong way here. Can you have pressure without current? The answer is yes, but it's all predicated on electrical pressure or voltage, okay? Just going to take a quick look at our Q&A just for a moment, see if there's something. Okay, good. We're doing good. Again, thank you guys for your help with figuring out our presentation here. All right. So we figured out what voltage is. Now we're going to talk about the notion of voltage drop. And what exactly is that? Why are we always talking about it? Why is it important? Same thing with the hydraulic analogy. Here we have a water pipe. There's water, some kind of liquid flowing inside this pipe. It could be a fluid of some kind, let's say. And you can see that there's a relatively high pressure on the left side of the pipe, but a lower pressure on the right side of the pipe. And what's happening here, as the water is flowing, there's resistance to flow that takes place, which could be in the walls of the pipe. The liquid itself, the molecules of the liquid itself are rubbing against each other, creating its own hydraulic resistance. Consequently, there's an energy loss that takes place. And that means that you're going to have a higher pressure here, and that pressure is going to decrease as you go further down the pipe. Thus, the need for lift stations sometimes in long pipeline runs and things like that. Okay. But what is this? The pressure is being reduced. What is that energy, that potential energy being converted into? And the answer is heat. So anytime you run a fluid through a pipe, and let's just say a crude oil pipeline is a really good example, the hydraulic resistance of the pipe itself and the molecules of oil and so on and so forth, they're going to generate heat that then has to be rejected somehow. But when oil flows through that pipe, it's flowing from a higher pressure to a lower pressure. and there is a pressure difference taking place there. What if that same pipe, suddenly the observer sees that the pressure is the same here on the left-hand side as it is on the right-hand side? What if? What does that mean? What does that tell us? Well, there's a guy named Blaise Pascal that described this quite nicely. And what he said was, in a confined fluid, if there's no pressure, pardon me, if the fluid is confined, it's not moving, and it's under pressure, you'll be able to measure the same pressure throughout the system. So what this is telling us, when you have the same pressure here as we have on the right-hand side, it's telling us the fluid is not moving. There's zero flow. And it's the same thing with electricity. If we measure zero voltage difference or voltage drop across a conductor, for instance, it is telling us that there's no current flow taking place. So what I like to do with my students, if I'm doing a live class, is we have electrical boards and power supplies and things and DVOMs. And I get them to experiment themselves and figure out if indeed what I just said is actually true. So when I make an assertion like this, and I say when current is flowing, a voltage drop will take place across any 2 points in the circuit, they take this electrical circuit and they start by turning on, having power turned on in the circuit. So S1 is switched on, this S1 is closed, and electrical current is passing through from B plus, flowing through the circuit, back to chassis ground, and then to the battery negative post here. Okay. So we have electrical current flowing. What do you expect to see if everything is normal? What would you expect to see for a voltage difference between these 2 points? And on the boards that I use, 1.7 millivolts is a number that would be expected on this, say for a 16 gauge wire with maybe 2 amperes flowing through it. Regardless, this is telling us that there is current flowing in the circuit with that potential difference going on, not source voltage, right? But potential difference of this magnitude is telling us there is current flow in the circuit. Now, what if we turn off the power to this circuit? So switch S1 is now open. There's no electric current flowing in the circuit. What do you expect to see, what is your voltmeter going to tell you when you make this measurement? And the answer is 0.0 millivolts. In other words, there's no voltage difference between these 2 points. This is just like the pipe filled with oil. The pressure here on the left with the red probe is the same as the pressure being measured on the right probe. There's no difference between those two. And consequently, this is telling us that you have no current flow in the circuit. Now, moving on to why we want to do voltage drop testing in the first place. What is it that's going to make us go there? Well, here's the customer complaint. You have an electrical component that is underperforming. It is performing, but is underperforming. It's not doing what it's supposed to do, or it's not supposed to be, pardon me, it's not performing as well as expected. And now we're potentially going to be looking for voltage drops. Let's talk about that. So this could include things you could be chasing down, or pardon me, customer concerns that you could be chasing down could include dim lamps, slow motors, or weak heaters. These are just 3 examples of things that a customer might have a concern with, and you are now charged with figuring out, well, why is it that these loads are not performing correctly? Now, there are folks who are tempted, and sometimes they're right, they're replacing a component, assuming that the component is the failure, that the component itself, a slow motor, for instance, okay, the motor is turning slow, must be a bad motor. Let's change out the motor. Maybe they're right. However, if they're wrong, that could be a very expensive mistake. We need to give the component the benefit of the doubt, is what we need to do. And the first check with a concern like that, the very first check should be what voltage is actually appearing at the component itself. So the technician's first check should be to confirm sufficient voltage at the component. Now, you're going to want to make sure that the battery is also providing the correct voltage first, okay? But then how does that compare to the voltage that the component is actually seeing? Is that going to tell us about why the component is underperforming? And in order to do this testing, the circuit must be energized. So anytime you're doing voltage drop testing, the component is turned on. It's energized, and now you are actually measuring live voltages throughout the circuit. So that's the very first rule of voltage drop testing right there. The circuit has to be operational when you're doing these measurements. So first question, to measure voltage drop, the voltmeter is always connected in how with the circuit, parallel or series? And the answer is parallel. Keep in mind that your voltmeter, your digital volt ohm meter, you are going to be connecting it across components and across conductors. You are not disconnecting things and putting it in series. If you were measuring amperage, that's the way you would do it. But when you're measuring voltage, all you were doing is taking that voltmeter and connecting it across specific areas of the circuit and certain components within the circuit. Now, yes, you are creating another path for current to flow. However, keep in mind that a digital volt ohm meter has what's called a very high impedance and is going to draw a very, very, very small amount of current through it in order to take that measurement. Effectively no current on a, just on a pragmatic level, okay? So your voltmeter is again attached in parallel to make this measurement. Here we have a basic electrical circuit, and it has the primary components needed to make it functional, starting with a battery power source here, feeding the positive lead of that, feeding into a fuse or circuit protection. I had a discussion in one of my classes not that long ago. Is the circuit protection critical to the operation of the circuit? The answer is yes. Will it work with the fuse bypassed? The answer is yes. This remains a critical and non-negotiable part of the electrical circuit right here is your fuse or circuit breaker or whatever it is that's being used for circuit protection. That has to be there. Now, your switch is downstream from that. That's your control switch, turning the circuit off and on. And then that feeds into a load. In this particular case, it's a lamp. And that represents the majority of the resistance in the circuit right there. Not all of it, but the majority of it. And then finally, the electrical current will leave the lamp. It's going to pass down to ground and then return to the battery negative via the ground side of the circuit. Now, we've got a problem. The bulb is dim. It is not performing up to expectation. One of your first clues as to whether or not the battery is a problem is going to be, hey, is there anything else that's dim too? Okay, but if it's one bulb that's dim, the rest are working fine. Well, you've confirmed the battery's working fine. But we take a measurement, and here we have 12.6 volts across the battery. But then when we take a measurement at the bulb, we see we've got 8 volts. What could be the problem? Where did the 4.6 volts go that we're not seeing? We should be seeing 4.6 or maybe 4.4, something like that. Pardon me, that's not right. I said that exactly wrong. Okay, you got 12.6 at the battery, and you should expect to see close to battery voltage across that bulb. But the question is, where did the 4.6 volts go that the bulb's not seeing? because now with 8 volts, yes, indeed, that does describe or explain why that bulb is dim. So what do we do next? First things first, assumptions, understanding of what's causing this in the first place. Anytime you send an electric current through a resistance, there will be a voltage drop that takes place. So in other words, you will have voltage drop throughout the circuit, okay? Because there's resistance in all parts of the circuit. The question is it excessive resistance? So voltage drop is always going to be the amount of voltage drop that takes place is going to be in direct proportion to resistance. As resistance goes up, it's going to create more voltage drop. It's going to consume energy that now is not available for the load. So what does this look like in real life? Okay, loose connections, corroded connections, frayed wires, just like the description there, the illustration on the right shows a wire that still has continuity. It still allows electric current to flow, but there's only one strand now allowing that current flow instead of a bunch. That's going to have a direct impact on actuator performance or load performance. Another one is burn contacts. That's inside stuff, right? It's hard to inspect, except if you got enough heat being generated and now it's melted things. But burn contacts in a relay or solenoid or a switch. This is another possible place for voltage drops to take place. But it's all related to excessive resistance. Here's a statement from an electrical training manual that I saw in the recent past. And what it said was, remember that for a circuit to function, it will need a no resistance connection to protected power and ground and a resistive load. The load should be the only resistance in the circuit. And if you think carefully about this, if you have better information, and I say that with love and respect, okay, well, the load isn't the only resistance in the circuit. Now, the other resistances should be low, but they are not no resistance. We need to make absolutely sure that everybody understands this. So instead of no resistance, it should read low resistance. And instead of the being the only resistance in the circuit, okay, now it's the majority of the resistance in the circuit. The load should be the majority of the resistance. And then things start making sense when you start looking at what a voltmeter is going to tell you when you're doing measurements on a live circuit. Keep in mind that all conductors, all of them, have resistance. And some conductors are better than others. Silver is an outstanding conductor. Obviously, it has some challenges in terms of, could we use this, as a common conductor in machines and so on. Obviously, the expense is way over the top. Not going to help on that front, or is less suitable for sure because of that. The other thing about silver is that it oxidizes very, very rapidly. Anybody who owns silverware, like real silverware, for your dinette or your dining room, well, you're polishing that silver consistently because it oxidizes that quickly. Copper is an outstanding conductor. It's not as good as silver, but it is pretty much the foundation for our electrical systems worldwide. Every application you can think of, copper is going to be the number one choice as an electrical conductor. Reasonably low price, although the price has increased significantly here in the last year or so. Certainly, copper can be soldered. It's malleable. There are a bunch of other properties that make copper the first choice for the majority of the conductors that we have out there. Now, gold. A lot of people think that gold is a better conductor than silver or copper. That's not the case. But the one thing that gold has going for it, in particular, is it won't corrode. So consequently, we use gold-plated terminals in safety-critical circuits such as airbags and so on. And that helps assure that the airbag circuit is not going to be compromised and then lead to a situation where, say, it doesn't deploy when it should. So that's gold. Obviously, we're going to use gold in very, very small amounts just because, well, it's now over $4,000 an ounce. That might certainly the bean counters within your organization aren't going to like the idea of using gold extensively for an electrical conductor. And then finally, there's aluminum. Aluminum, what does it have going for it? It's light, it's cheap, rejects heat really well. Some of the things that aren't so good include it's not malleable and like it's brittle, relatively brittle. Another thing that is a strike against aluminum is that it doesn't play nice with other materials that it's connected to. So oxidation of, connections where you've added, tin coated terminals and things like that. Aluminum doesn't play nice with that stuff, and there has to be measures taken to deal with that. Aluminum having a higher resistance. Also, if you were going to replace a copper conductor with aluminum, you would need a significantly larger aluminum, like in terms of cross-sectional area. The issue, if that's what we're worried about, why don't we just use an ohm meter to track down where the resistance is taking place? Seems like a more direct path, right? The ohm meter will measure in ohms, and you just look for higher ohms, okay, where it's not supposed to be. Consider taking your ohm meter and measuring the resistance of a fuse and what the ohm meter is going to tell you. So in this case, we took a measurement, like an ohms measurement, as you can see on the meter face. We're taking an ohms measurement of that fuse, and it's telling us 0.0 ohms. Some would interpret that to mean that the fuse has no resistance. Is that the case? The answer is no. The fuse does have resistance. Now, you should keep in mind that the meter is not lying to you. The problem is that the meter doesn't have the resolution to be able to express the real resistance of that fuse. So if you actually wanted this meter to tell you what the real resistance of the fuse is, you would have to have 3 and 4 more zeros after the decimal point in order to get to where you can actually measure the real resistance of the fuse. So what's a more practical way, if an ohm meter isn't going to work, if it doesn't have the resolution, what's a more practical way of determining where the resistance of the circuit is? All right, here you go. Voltage drop across the fuse, okay, would be a great example of how this works. So if we take the same fuse, this meter said 0.0 ohms, and we say to ourselves, well, that has no resistance, put it into an electrical circuit where there's current flowing, then you see something different when you measure voltage difference across it, or voltage drop. And here we have 8.2 millivolts of drop going on across this fuse, telling us what? Telling us that we have electric current flow through the fuse. And it's actually possible, and this idea has been around for a long time now, the business of estimating the amount of current flow through that fuse can be achieved by doing a voltage drop test across the fuse, and then knowing the type of fuse and the rating of the fuse. That can all be plugged into a chart. Power Probe has a chart that they publish online, and use that chart to estimate the current flow through that fuse. Pretty handy diagnostic tool or diagnostic procedure for, say, narrowing down parasitic drains and things like that. The main point is the fuse has resistance. And when you send electric current through the fuse, there will be a voltage drop that takes place across it. So here we have a DVOM, and it is measuring voltage across a fuse. And this is the reading that you're getting. What is this telling you? Is there current flowing in the circuit, or is there not current flowing through the circuit? And the answer is current is not flowing in the circuit. If you're taking a voltage measurement across a fuse and you get that for a reading, it's telling you there is no there's no current flow in the circuit. Okay. Back here, different story. Now there is current flow in the circuit, And the amount of voltage drop that's taking place is going to be in direct proportion to the amount of current that's flowing through it. Okay. Next question. How much voltage drop is too much? And guess what? There's a little bit of subjectivity involved here, meaning different applications are going to have different acceptable voltage drops. The numbers that you're seeing there are just total rules of thumb. That's all. Okay. They are not hard and fast numbers by any stretch of the imagination, but it's giving you a little bit of an idea on a 12-volt automotive circuit. Okay, what is normal voltage drop on the power side of the circuit? So if you're measuring from the positive side of the load to the positive battery terminal on the battery, when it's in operation, you should see 250 millivolts or less for voltage drop. Notice that the ground side of the circuit, you should expect less voltage drop on the ground side. Why is that? Well, for one reason, typically you have fewer connections and contacts switches on the ground side of the circuit. Okay. It's a less cluttered section of the circuit. So typically we would expect to have less voltage drop on the ground side. Now, again, let me reiterate, these are not hard and fast numbers. Also, if you have a 24-volt system, okay, this is for 12 volts, right? If you have a 24-volt system, you could expect these numbers to be twice what they are. So in other words, if you have a 24-volt piece of equipment, well, you could expect normally 500 millivolts or less on the power side and 200 millivolts or less on the ground side. Ballpark numbers, okay? So here we have a parallel circuit. And this parallel circuit has three branches. All three of these branches, if everything's working correctly, all three of these branches in a parallel circuit should be seeing the same voltage or close to the same voltage. Now, we've got L1, lamp 1, which has a ground side switch. That switch is open. There's no current flow going through L1. However, L2 and L3 both are the same brightness, okay? So there's no difference in the symptoms between L2 and L3, but L2 has a resistance on the power side, and L3 has a resistance on the ground side. So now, in practice, how is it that we're going to figure out, okay, these are underperforming loads, is what they are. Both these lamps are dim. Just looking at them, there's no way to tell whether it's a power side failure, high resistance, that is, or ground side high resistance. We're going to have to bust out the meter and see what happens here, okay? We're going to start by measuring voltage at the source. So you guys can see that this source voltage in this particular case it's being fed 11.96 volts at the B plus terminal and the negative terminal down below on chassis ground, we'll call it. Now, our next measurement is at bulb L2. Does this explain why the bulb is dim? The answer is yes. The bulb does not have what it needs to do its job. It's only seeing 2.96 volts, let's say 3 volts. There's 12 volts at the source. There's 3 volts at the bulb. Where did the other 9 volts go? So now we have to figure out, okay, is it a power side problem or a ground side problem? It could be both, but not real likely. Let's do some measuring here and find out, okay? So number one, we'll take our negative probe from the multimeter. We're going to attach it to our negative, that is, the negative post of the battery would be best, for sure. And then take the positive lead from the digital voltometer or voltmeter and get onto the positive side of lamp L2, and we're only seeing 2.98 volts. Is that adequate? The answer is no. What should we be seeing? We should be seeing close to, we won't see source voltage, but we should be seeing close to source voltage. We're not. Clearly, we got a problem on the power side of that circuit. Just for our own information, let's test the ground side. And what do we see on the ground side? So you take the red lead and move it to the ground side of lamp L2, and you see a voltage drop of 1.2 millivolts. What does that tell us about the resistance on the ground side of the circuit? Obviously, the resistance is very, very low on the ground side. It appears to be fully functional. Our problem is on the power side. So now we got to narrow it down. Okay, so now we know, okay, it's that law of halves, right? We've determined, we've cut it in half. Lower half is fine. Let's go to the upper half and figure out, okay, where specifically is this problem taking place? So we start doing voltage drop measurements across things like your fuse holder and things like this. Okay, so our fuse holder in this case has a voltage drop of 6.5 millivolts. Is that unacceptable? No, it's just fine. There's no problem there at all. Is there resistance there? Yes. Is it unacceptable? Not by any stretch. Let's measure the switch. 5 millivolts. Is that a problem? Not by any means. Okay, nothing wrong with that. The conductor leading from the switch down to R1 there, okay, and you're seeing 2.3 millivolts. Is there a problem there? It's here where we take this measurement, and now we see that we have a voltage drop of close to 9 volts. This is a ridiculous example in the sense that if there was actually a 9-volt drop taking place there, you'd be generating an enormous amount of heat, and you'd probably figure out pretty quick what was wrong because there'd be a fire. It's probably how that would go. However, on the board with a resistor that can reject a certain amount of heat, okay, this is what the voltmeter is telling us, that we have a problem here. R1 clearly is where the problem is, and that is why lamp L2 is only seeing 3 volts, because 9 of those volts are being consumed, being converted into heat by resistor R1. Let's take a look at L3. It has the exact same symptom as L2. It's the same brilliance as L2, okay? But we start by looking at the positive side of the circuit. So we have our negative probe over on the lower left, and then we move our red probe to the positive side of lamp L3, and we measure very close to source voltage. Is there a problem on the positive side of the circuit? The answer is no, it's fine. Let's take a look at the ground. So we move the lead to the ground, and now there's an 8.97 volt difference between the ground side of lamp 3 and the battery negative post. Is that a problem? Yes, indeed, it is a problem, and would explain why you're only seeing 3 volts across L3, because 9 of those volts are being consumed by this resistor R2, and it is converting that lost energy into heat is what it's doing. Okay, but that's directly impacting the operation of lamps, in this case L3. All right, so that's how we narrow down whether it's on the positive side or on the ground side, and how that's impacting the circuit. Okay, so yeah, we just narrowed it down. 9 volts across resistor R2. That is a problem, no question. People spend a lot of time slagging the power probe, and I know why. And the problem is not the tool itself. The problem is a lack of education, because people go nuts with the power and ground switch that's on this thing, and they inject 12 volts and grounds into places where they shouldn't because they don't understand what's going on, and then they let the smoke out of the box. And this sometimes leads people to say power probes are bad. And guess what? Power probes in my world are the best thing, one of the best things that's ever been invented. And the reason I say this is because it is always taking measurements with the battery itself as the point of reference for all the voltage measurements. That is the best attribute of the power probe. All of your voltage measurements are being made with the battery itself as the point of reference. That's huge, absolutely huge. Okay. The use of the power probe, again, forgive me, the majority of you folks are very familiar with how this works, but you connect your power probe to your battery power, and directly, right? So you've got your positive right on the battery positive, and you got your negative right on the battery negative, or close to it. It'd be even better if it was right on the post itself. Okay. But anyway, you go to take a measurement. Here you have, if you take the power probe now and put it on the battery positive post, you see there's a little red positive sign that's on here telling you this is illuminated, telling you you have good battery positive power here. Where if you go on to the negative post, it immediately tells you that you have a good ground here. Okay, so this thing can narrow down very quickly whether it's a positive side problem or a ground side problem. And if you just used it for this, don't mess with even if you didn't even if you put a piece of tape or something over top of that rocker switch, this part of the tool doing the measurements with the battery as a point of reference, that's the best attribute for the power probe. Now, so here's a little bit of a close-up of what you see illuminated when you have good battery positive power and what you see when you have a good ground. Now, here's our power probe on the series circuit. You saw the series circuit once before. Here it's back again. And here's our power probe taking a measurement at B plus. You're seeing 12 volts on the readout, and you're seeing this red plus sign illuminated telling you you have good battery positive voltage there. We move it down to lamp L1. Okay, keep in mind, okay, what I'm showing you here is 3 lamps that are in series. They're all dim. We already know the reasons why, okay, but we're going to take some voltage measurements with the power probe and see what it has to say. So what are you going to see here? Well, you're going to see 12 volts, and you're going to see that it has good battery power at the upstream side or the positive side of L1. Now, we move it to the positive side of L2. What are you going to see? Now, if all 3 of these are the same wattage, basically they're going to be sharing the 12 volts amongst each other. So this is going to consume, L1 will consume 4 volts, L2 will consume 4 volts, L3 will consume 4 volts. So what is the voltage difference between here and the battery negative at this point? The answer is 8 volts. So there's 8 volts of difference between the battery negative over on the lower left, okay, and the point that the power probe is connected to. Notice that we don't have good battery positive voltage here, and we don't have a good ground. Neither one of these lamps is illuminated. Okay, so that tells you right away, okay, we're somewhere in between. We might have a problem here. Okay. L3, what are you going to see here? Keep in mind, you've dropped 4 volts across L1. You dropped another 4 volts across L2. L3, you're going to see 4 volts. Is that a good ground there? No. Is that good battery positive voltage? No. Telling you there's something up here. What is going on? Okay. Finally, notice that S2 here is closed, effectively bypassing R1. Okay. What do you think the power probe is going to tell us at this point? And the answer is it's going to tell us you've got a 0 volts difference, 0.0 volts difference between this point and the battery negative here. Okay. Keep in mind, it's just a single digit after the decimal point. Okay. It would read something different if it had more zeros back here, but it's not made for that. It's telling us we have an adequate ground, right? Take a digital voltometer, make the same measurement. Now you're going to see something to the magnitude of 0.06 volts or 60 millivolts, which would be perfectly acceptable voltage drop. Okay. Open up S2. Now what do you see? Is there going to be a significant voltage drop taking place across R1? The answer is yes. And we see that there's a 7 volt difference between where the power probe is contacting here and the battery negative. So we've got a serious problem going on. If we thought this was supposed to be a good ground, it is not a good ground. We've got a 7 volt drop across that, and this resistor is the problem. Okay. Notice again, the green negative is not lit, the red positive is not lit. It's somewhere in between. There's something going on there. Okay. Okay. Voltage drop testing in heavy duty starter and alternator circuits. For the longest time, I'm thinking 15 or 20 years now, we've been kind of shunning our carbon pile testers. And they may be collecting dust in the back of the shop. They maybe have been thrown out and not be there anymore. Let's just say if you still have yours and you're considering throwing it out, don't do that. Don't do it. Okay. It wouldn't be prudent. And here's why, because that carbon pile tester can still be used for some good basic testing, particularly related to voltage drop testing on starter and alternator circuits. And we're going to talk about that in terms of heavy duty vehicles. So here we have a starter circuit on a Class 8 truck. It's got 4 batteries in parallel, 4 12-volt batteries in parallel, so it's supplying 12 volts to the system. And you'll notice that the carbon pile has been attached across the starter. So when you actually operate the carbon pile and start drawing electrical current through the carbon pile, what you're doing is drawing current from the batteries through these cables, and then you're using voltmeters here, or a voltmeter, to measure the voltage drop that takes place on the ground side, and you're using one to measure the voltage drop on the positive side. Now, the reason that this is such an elegant test is because if you're cranking the engine to try to generate your current flow through those same cables, well, the current flow is constantly changing. The moment that you engage the starter, you have that inrush current that takes place. There's an enormous amount of current that flows into the starter. And then as the engine starts to turn, the current drops and then rises every time it comes up from compression on another piston. What I'm saying is that the current draw through trying to do voltage drop testing with the current draw going all over the place, not that useful. How about we do it in a controlled way with the engine off, with the key off as well, and just use a carbon pile to draw current through those cables and measure our voltage drop that way. Engine's not turning over, don't need another person to crank it, just an elegant way of going about things. So this is a method of testing the starter cables, right? Running from the battery to the starter, right? There are some excellent instruments out there that can be used to do this test, like an automated and even guided testing here. This one is not being built anymore, but there's ones that are built by Midtronics and Autometer that do everything this one does and better, okay? So take a look at this, where now we're testing the cables and the ground connection to the alternator as well here. And notice that the carbon pile, what we've done is we've attached it to the B plus terminal on the alternator and the frame of the alternator. Okay, in order to draw electric current through the cables and the ground connection running to the alternator and make sure that it's working correctly, that there isn't excessive voltage drop in those cables. When we draw that electric current, notice that we're also simultaneously measuring positive circuit loss or voltage drop, and we're also measuring negative circuit loss or voltage drop. And we're confirming that the cables and connections running between the battery and the starter and alternator both are adequate to do the job that we need done. Okay. So here we have the instrument that I showed you a picture of before. Here it's connected across the output terminal and the frame of this alternator. There's 2 leads that come off that tester that run to the battery itself. So here's the battery pack itself, and it's measuring voltage here with current being drawn through the cables using a load that's attached to the high current cables here that we've clamped onto the alternator. So basically, it's not a carbon pile, but it's something similar. It's drawing current through these cables. All that same current has to leave the battery here and pass through the cables, and we're measuring the voltage here compared to the voltage here and looking for resistance using voltage drop. Okay. This is the report that comes back. The report comes back saying it passed at 160 amperes. So what we were doing was testing the alternator cables, and we told it that the maximum output of that alternator was 160 amperes. So it tested it at 160. It's telling us that it's good up to close to 300 amperes, that it had a 0.21 volt positive voltage drop and a 0.06 negative voltage drop. Perfectly acceptable. Okay. This is another unit that can do all kinds of neat tests. It also has a remote head that you can be carrying and be in various other places in the shop while the test is going on, maybe in the cab, for instance. And it records it all for you. It draws graphs for you. It does all kinds of cool stuff. Anyway, it's basically following through on the same kinds of tests that we just did using the carbon pile, just a little bit fancier and a little bit faster. Okay. But there are some dynamite tools out there for doing those kinds of tests, and you might consider making that investment. So we got 5 minutes left. I'm going to take a quick look at our Q&As here just to see. Okay, so we've got to be doing okay. I haven't had any negative feedback here. Today's class, there is a post test. So if you have your phones, you can go ahead and scan this QR code, and it will take you to a 10-question quiz. Maybe I'll move that. Maybe that'll help. A 10-question quiz that will hopefully be informative to you. When you submit the form, when you answer all the questions and submit the form, it's going to give you a score, and then it's also going to give you a rationale for the correct answers. So, of course, that's optional, but if you care to, go ahead and scan that QR code and see how you do on the post test, which is all related to the material that we just covered in this class. Okay. So I certainly hope that this has been helpful for everybody. Thank you guys so much for your help with making sure that the presentation went good. And I'm assuming, because I'm not seeing any more in the Q&A, that things have turned out okay on that front. So glad everybody could make it to the class. If you have any questions or observations that you care to share, feel free to send me an email. This is my contact information, and I can get you an answer. If I don't have an answer, I can get you an answer. But hopefully this webinar has been helpful to you, and we certainly wish you guys a good day and a good upcoming weekend. So thank you very much for your time today, and hopefully we'll see you on Tech Tip Thursday the next time we present. So take care.